Okay, morning.
Morning.
Morning. What topic did we discuss last time?
We finished the circuit.
Parallel circuit, right?
Yeah.
And what topics before that? Okay, before that?
Series circuit.
Series circuit. So any questions about the series circuit and parallel circuit? Everything is good, right? You get 100. Right?
Maybe.
What we are going to discuss today?
Combination.
Okay, combinational circuit. That's easy, right? You just combine these two topics together. I suppose, right? You think it's difficult or not?
Well, we already know.
If you are very good at the series circuit, parallel circuit, and then combinational circuit is not very difficult, right? Okay, first one, we have this. I want you to connect in a series. How to do this? Alright, that's easy, right? So we just head to tail, connect all together. Right? This one is good. Series circuit? Yes. How many loops do we have?
One.
Only one, right? If we add a source, we have only one loop. Next, we want to connect these three in parallel, right? So that is how we connect in parallel. How many nodes do we have? 2. Not 6? Not 6, right? We have only 2. The left hand side, all these are 1. So 1, and on the right hand side, there's another one, so that's 2. For any parallel circuit, we have only 2 nodes. For series circuit, we have only 1 loop. Most practical circuits are not as easy as this. Usually they are combinational circuits. That means series circuit and parallel circuit all mixed together. To analyze combinational circuit, we need to have a new concept called the equivalent circuit. That means two circuits are electronically identical. Not physically. They may have different in physics, but they are electronically identical. An equivalent circuit is one that has characteristics that are electrically the same as another circuit, but is generally simpler. The equivalent circuit concept will be used all across the curriculum. So you are going to see this. What is the equivalent circuit of this? What is the equivalent circuit of that? A lot of times. This one. We have 2 resistors in series. Right? One is 1K, another one is also 1K. Is equivalent to what? We want to make this circuit simpler.
2K.
2K, right? Okay. We have only 2 resistors here. Make it simpler, that means we need only 1. So you may already have a picture in your head that that is the simplified equivalent circuit. So that is 1K plus 1K equals 2K. That's it. Very simple, right?
Yes.
Right? And if you think these 2 circuits are black box, you only see the 2 terminals, right? These 2 terminals, these 2 terminals. If you have a meter, wattmeter is ohmmeter, or no matter what, you try to measure this electrically, you cannot distinguish which one is which. That means you measure the voltage. If you connect the source, they are the same. If you measure the resistance, they are the same. If you measure anything, electrical properties, all the same. So that means we do not know, we cannot distinguish these 2. That's called the equivalent circuit. Okay, now this is these are 2 resistors connected in parallel. I want to simplify this into only 1 resistor, definitely. So can you, first one, let's imagine what you have. So you must have only 1 resistor, right?
Yeah.
Right? You need to mark the value. What is the resistance?
2K.
1, 2K. Someone says 1, someone says 2. Any other options?
It's
Half K.
0.5K.
So now 25K.
No, 0.5.
0.5K. Okay, we have 3 options. Okay, 1, this 2 and half. Let's vote. Which one? You think it's 1? Who agrees with 1?
Nobody agree?
No, okay, you are the only one. Okay. Who agrees with 2? Somebody is the only one. Right? All others are half or don't know. Half. Okay, half is good. Why is half? 1 and 1 in parallel. How to calculate the parallel value? 1 times 1 divided by 1 plus 1. Right? So which equals half. So now you have a picture of this. That looks like this. 500 ohms, 0.5K. Right? Good. Again, there are no electrical measurements that can distinguish the 2 boxes. Right? They are called what? Equivalent. Now another example. This one. Well, let me ask you. These 3 are connected in parallel
and series.
and series.
Yeah.
So it's not a series. It is not parallel. This is called a combination. Right? Means a series and parallel. Okay, so can you imagine the equivalent circuit? Now we have 3 here, right? Okay, first one make it a little bit simpler. We reduce to 2. So which 2 you want to combine? R1 and R2. You want to add these 2 together, right? So it will be 3.7. Good. So now you imagine this. You are going to have a 1 here. We can call R1, 2. Right? Combine together means make it simple. Then another one in parallel, which is 4.7.
3.7.
Then what's next? Make it even simpler.
1 over 3.7 plus 4.7.
So we have 2 combined right now in parallel. One is 3.7 and another one is 4.7. Then we go further,
Okay.
which is only 1, right? What's the value? 3.7 times 4.7 divided by 3.7 plus 4.7. Right? You have calculator, you can do this, but right, that's the first one. We are good, right?
R2
And the next one will be
over 1.
2.07. We just use the 3.7 times 4.7 and then divided by the sum of these 2, we get 2.07. Now we have 3 boxes. These 3 are equivalent. Right? Yes. If you measure any pair of terminals electrically, you cannot distinguish between this. You don't know if there are 1 inside, or there are 2, or there are 3. Or more general, there are many. We don't know that. We only know. So the equivalent resistance equals 2.07. That's the only thing like this. Right? If you measure the resistance of the first box, what is it? Suppose now you have the ohmmeter, right? You measure the resistance. We in the which one homework we test you how to measure the resistance, right? You know that. So you just put the 2 terminals. First one, you need to disconnect the circuit from the source.
Yeah.
Right? Then you put the 2 terminals, the 2 probes to the 2 terminals, and you measure the first one. What is the resistance? What's the reading? Oh, looks like we don't know. Now look at the third one. What is it? 2.07. That's easy, right? Now what's the second one?
2.07.
Why?
Because
Because they are equivalent. They must be the same. Now, how about the first one? 2.07. They are exactly the same thing. Does it make sense? That is the concept of equivalent circuit. If you measure the resistance, they must be the same. Others like voltage or current, all the same. Any electrical property will be the same. So there are no electrical measurements that can distinguish between these three boxes. Right? So to us, just black box. Okay? We only see this pair of terminals. We don't know what is inside. We may have more. We know Kirchhoff's voltage law. What is it? Anyone? I'll ask somebody. Can you tell me what is Kirchhoff's voltage law? All the voltage drops add up together equal to zero. What is Kirchhoff's current law? All the current
Entering and leaving a node equals.
Oh, yeah.
Okay. All the current entering the node, any node, equal to sum up together equal to zero. Right? We said Kirchhoff's current voltage law applied to what kind of circuit? Series circuit. And current law applied to parallel. Any? Oh, don't look at this. No, we haven't into there yet. Right? We review to parallel circuit, right? And that is before. Now you already know this. These two laws can apply to any circuit, combinational circuit. But keep in mind, when you use KVL, you still need to use it to a closed loop. You cannot use to any arbitrary. You need to apply to arbitrary, but it must be a closed loop, just like a series circuit. For Kirchhoff's current law, again, you can apply to this combinational circuit, not necessarily only parallel, but again, apply to a single node.
Okay.
Then all the entering current add up together equal to zero. Keep these two in mind. Now look at this. This circuit definitely is not simply, it's not just the series circuit or parallel circuit. It's combination. Right? Look at this. We can trace the outside loop. This one. This part is series. And this is a closed loop. So we can use Kirchhoff's voltage law, not current law, right? Current law applied to a node. We always keep in mind it. Right? Closed loop means we are going to use a KVL. Right? We start from the left bottom. Right? We start from there. Then the first one, the source, 5. We are going to write what? 5 or negative 5? I'll give you a hint. It's 5 or negative 5? When you write the KVL, right? You need to write the sum of all the voltage drops equal to 0, right? Something plus something plus something equal to 0. That is the law. Okay, we start from that part, the corner. Then you go to the first one, that is the source. The source looks like 5 and the positive is on the top. So when we write the source, that number is 5 or negative 5? Negative 5, right? We always use the starting minus the ending. So we use the negative minus the positive. So that is negative 5. Then plus looks like the voltage on R2. And we can imagine the current flowing this way, right? Flowing this way, so the top voltage will be higher than the bottom. Right? So the voltage here will be higher than this one. So we go this way, that means this voltage will be a positive. Make sense? Right. So this negative 5, then plus this something here, it's positive number. Then plus this one. This one is also positive. This one minus this is the voltage drop across R4. Then plus this one, the voltage drop across R5, which is from here. This one minus this is positive. Then plus this one minus this, which is the drop on R6 in this way. Right? Then nothing else. So all these are 1, 2, 3, 4, 5 values, voltage drops add up together equal to 0. So that is the KVL for this closed loop. Any questions on that? Can you give me another one? Okay, first one, let me ask, how many do you have? This is 1. We work together. How many can you?
3.
3?
3 closed loops, 4 closed loops, 1, 2, 3.
3 independent. But if arbitrary, there will be
4.
4, 5, 6. Finally, 6, right? You guess, right? Good guess. Alright, so look at this one. This is 1, right?
Yeah.
And this is 1, right?
Yes.
And this one we just mentioned, so 3, right?
Yes.
Okay, now we start from here. This is 1, right? Okay, then this is 1, right? So that's
I guess.
2, 3 plus 2, then the last one. 6, right? 3 plus 2 plus 1. We have 6, right?
Yes.
You said 3. I don't blame you. That is correct. 3 independent. That means this 6, there are 3 independent. There are 3 dependent. The 3 dependent can get from, you can close your eyes, manipulate the other 3, you get the other 3. So that's, later time when we study 110 or 111, we are going to use, in this case, we are going to have 3 independent. We do not use 6. If you use 6, you are going to have a trouble. Right? So you have use this one, this one, this one. Very straightforward. But that is the story next semester. All right? This one here, I asked somebody to give me, for example, this one, the last one. How are you going to write the KVL? This minus this, right? The voltage drop going up, then plus this one, plus this one, plus this one, equal to 0. Right? So that is the KVL. KVL. So now this is the second, also works. And this one is the KCL. KCL applied to a node, a single node. Again, later time you're going to super node. Super node means a lot of nodes combined together, but still considered as one. In this case, let's see. We have 5. This is meter here. What are the readings for node A here? So this reading, current going in, right? Because this is positive. And this will be negative number, right? Because this current going this way, and this current going this way. So if this current plus this current plus this current going up, what is it? 0. Right? So all the current coming into this single node will be equal to 0. That is the KCL. How about this one? This current going down, this current going left, this current going up, these 3 add up together,
0.
also equal to 0. Right? Alright, so the numbers, the first one is 8. Alright, now I'll ask what is the number, what's the reading on here? Look at this carefully. Pay attention to the polarities, positive, negative. What is the number here?
10.5.
10.5. You mean 26?
Oh, 26, yeah.
Pay attention to the polarities, the direction of the current flow.
They both were plus, so you have.
This current means flowing this way, right? This one flowing down. So this current will flow this way, right? And this is positive, so that will be the sum of these two. So it's 26.5.
Go.
Make sense?
Yeah.
How about if I change the polarity of these two? So this one is negative, this one is positive.
You subtract.
If this is DC, then we are not allowed to do that, right? In the labs, you know this? You already know this, right? If this DC is here, you are not allowed to connect in the reverse order. So this one must be positive, this one is negative. And that is the old needle type of matrix. But if you use the digital, you can, but the number will be a negative. The negative, that means you are in the wrong direction. So, but the number is still good. Okay. That's 26.5. Right? Good. Now we have this circuit. Again, we want to tabulate this all these numbers. What we are given is the source equals 10 volt. R1 equals 270, R2 equals 330, and R3 equals 470. Listed here, and the source is here. So we want to analyze this circuit. That means we want to know everything. All the resistance, the voltage, the current on each of the component. Which one you are going to start?
Add up all the resistance and get the total resistance.
So which one? This one, right?
Good.
So what is RT? Everybody, I want you to get a piece of paper to do this.
It's 1,070.
How will you get this?
I have it now.
Add this all together.
1,007.
1,070.
Okay, let me remind or give you a hint. This RT, total resistance, or we call this equivalent resistance. From where? Looking from the source. For example, you stand at this source, looking to the right. What is the equivalent resistance? That is called RT. Does this remind you something? You cannot just add all these three together directly. Can you? Alright, so how to do this?
463.
You tell me how you do it first. Step one.
I did the equivalent circuit for the two in parallel and did like 330 times 470 divided by 330.
Okay, so you do this first, right?
Yeah.
You combine these two first as they are parallel. So the value of these two we call R3. So usually when you do homework or in practice, you write this R23. Means this equals R2 parallel with R3.
Okay.
I like you to write like as neat as this. 2R3 means 2R, or sometimes you can put a comma here, that's fine. 2, 3. So that one will be equals R2 times R3 over R2 plus R3.
Yes.
So that is the combination of the bottom two. And what is the total?
190.
The total will be this one
Yeah.
plus the first one, right?
Yeah.
You can write it together. So the total T equals R1 plus R2 and R3 in parallel. Again, this one is what I want. The total equals R1 plus R2 and R3 in parallel. So that one will be equal to R1 plus this 2. Then you plug in the numbers you calculate. Anyone get the number?
463.9.
463 something. Okay, 464. Perfect. What else? Which one?
Now we go for
Which one next you want to calculate?
the curve,
The current. We have 4 currents. Which one?
the total.
The total. Okay, perfect. It looks like. How to calculate the total current? The total current means the current. Okay, the current here, right? Because the total. Look at the current will flow up and go down here, then separate two branches, then combine together, go back to the negative term. Right? So what is the total? That circuit looks like not series, not parallel. How to calculate the total? Give you a hint. We use the idea of equivalent circuit. Now, in our eyes, these 3 will be only 1, right? which is this value. Right? So what you see, this circuit is only the source here and only like this. That is the equivalent circuit of that one. So this one is RT, which equals 464. And this one VS equals 10. And this current is I2.
V over all.
So this one is much easier, right? Compared to that one. So that's why we need to spend some effort to reduce the circuit. Right? So this one. So what is IT? Right? 22, right? So 10 divided by 464 equals 20. I prefer 20 something.
0.02.
0.02. Okay, so 22 minutes, right? Is it good? Everybody get this result?
Yes.
Everybody need to feel good about this, right? You need to do homework by yourself and test. So everybody get this?
Yes.
Now this IT equals, let's see if this is the correct way. Step. Yes, perfect. 21 and 6. What's next?
All the currents.
All the currents will be the same.
Yeah. 21.6, all of them.
Yes? Yes? At least you have somebody agree with you. Wait.
Oh, man.
Okay, I mentioned this total current here going up is 21 and 6, right? Going down, this one, so definitely this one is 21 and 6. Now you need to separate.
All the voltage is the same.
We can use a current divider to do this, right?
Yeah.
But later time we find we have a better way to do this, okay? So if you write this one, I1 will be equals 21 and 6. But these two, not. We can use a current divider to get each one. Make sense? Alright. Now look at this one. Next one looks like we should calculate the voltage here.
Yeah.
Can we? Because we already know this voltage current here, right? See, this one is here.
So,
Definitely here you can calculate this R current 1 and 2 and 3, but that's not the best way. Right? Once we know this current here, can we calculate the voltage here?
Yeah.
Yes. So how to use that?
Equals IR.
Current times resistance. So this value times this one equals what?
5,800.
Okay, 5.8, 5,000 something millivolt. So 5.82. Perfect. What's next?
Find the I2.
Find
No,
I2. But this one, we put this at later time.
You could find the power.
Yes, we can calculate power, but we calculate this power all later time. Yes, definitely, you can. All we know this, we know all this, we can calculate power. Yeah, no big deal about that. You want to calculate 2 and 3?
It's the same.
They are the same. Okay, first V2 and V3 are the same.
Yeah.
Can we calculate V2 or V3? They are the same. Can we calculate them right now?
Yes.
How?
4.18, just 10 minus 5.
Equals this one? Okay, 10 minus this one, right?
Yeah.
Why? What's the theory? How do you know that?
Because voltage divider.
Voltage divider? That's not voltage divider.
Kirchhoff current,
The voltage law.
Voltage law, right? This voltage plus this voltage must equal to 0. So this is 10, this is 5 and 8, so we know this one. So 10 minus this. Yes, perfect. So V2 and V3 equals this and this. Both are the
How
same.
is the...
Yeah, because I decided.
Never mind.
Any questions on this?
No, I got it.
So far so good, right?
Yeah.
What's that? Look at this
We
here,
will
right?
find the current.
Then what's the next one?
Current.
Find the current. As we said at the beginning, we can use the current divider, but that formula looks like a lengthy, right? So here, look at this. We know the voltage, we know the resistance. Can we find the current?
Yes.
What law?
Ohms?
Ohm's law, right? Use the voltage divided by this equals this one.
12.7.
This one divided by this 12.7. Yes, that's close, right? That's possible. And this one divided by this equals this, right? So you can see R2, I2 and R3 are not the same. Right.
0.1.
You get it? This one, 12 and 7, 8.9. Good? Then next one, definitely we can calculate all this power. How to calculate power? How many methods do we have? 3. And voltage times current. Or voltage squared divided by this. Or current squared times this. Alright, so we got this, we got this, got this. And this one, same thing. You can use all this to calculate this, or you can add these 3 together, get this one. We are very familiar with all these techniques. Easy, right? Yeah. Okay, nice. The powers will be 126. That's we don't want to spend time to do this. You already know how to do this. But just be careful when you plug in, punch your calculators. Be careful, right? And this is 51, 53 and 1, and this one is 37 and 2, and the total is 216. Now I'll give you 10 seconds to review this. If you look at this, right, ignore all the red numbers, then you think where you start. Then one by one, how to figure out or calculate all these numbers. I remember there's homework, something like this before, but much easier than this. That is only a series circuit, right? This one is a combination, much more difficult than that one. But the ideas are the same. Give you a circuit, you tabulate all the possible values. And for example, let's check if the Kirchhoff's current law satisfies at this node. How to check this one? For example, if you are in the labs, they may ask you to check, to verify Kirchhoff's current law. Suppose I give you this circuit. You measure this voltage current here equals 21.6. And you measure this one, the current goes down and equals 12 and 7. And this one also goes down, equals 8.9. And so we have 3 current here. You add this positive going in, this one is negative going out. This one is going out also, so negative. So this one minus this equals 0. Hopefully. If not, that will be if they are not equal to 0, we call that as a error, right? That error must be very small. If that error is large, what are you going to do in your labs? You try again. If we try again, still that number, still very large. What?
Then it's broken.
Okay, the meter may be broken. These numbers may be not accurate. Right? So that is troubleshooting, right? Everybody should know the techniques. Right? So this is the Kirchhoff's current law applied to check the sum of the current must be equal to 0. Right? So this one. And also, the sum of the voltage, KVL, also must be satisfied. Look at this one. On the outside, this largest row. This one, we start from here, we go up. This number is negative 10. Then this one is so the negative 10, negative 5, positive 5.8, right? And this one, negative, positive 4.18, right? Then nothing else. These 3 add up together again equal to 0. This one is a voltage divider. Eh? It's not exactly the voltage divider we discussed before. The voltage, how to change this one to a voltage divider we discussed before. When I say voltage divider, you have an image in your head, right? What it look like? I'll give you this one. You say, oh, that is not. So how do you revise the circuit to make it a voltage divider we know before?
Change the bottom.
And you just remove this three, right? This R3 is gone, and this is voltage divider. Does that make sense? And the voltage on R2 will be equals to R2 over the total, then times Vs. Does that make sense?
Yes.
What is RT?
R1 plus R2.
R1 plus R2. That is what we discussed before. Right? Now we have this one, it's called loaded. That means we have a load here. Right? We need to connect this part to something. Because voltage divider, what does that mean? That means, for example, in your cell phone, right? Your battery, for example, maybe like 3.7 volt. And you need to, some IC may need like, for example, 2.5. I just make up some numbers. So how to get this 2.5 from that 3.7? Right? The ugliest method is use voltage divider. But that works. You use this one is 3.7, and this one is something, you choose the number, and this one is something, you choose the number you design, then you make this one equals 2.5. Right? So that is how you design this voltage divider. But as I said, this one is not a good way because that will waste a lot of energy. We have much smarter ways to get some fractions of voltage. That will be in high level classes, not in here. Right? But anyway, once we get this voltage divider, we need to connect this one to a load. Right? This load has a resistance. So that is called a loaded voltage divider. If you compare this loaded voltage divider, this is not exactly the same we discussed before. Before it's a series circuit. This one is a combinational circuit. This is not series. It's not parallel. This load is parallel with its R2. So how to find this voltage here? But I still want the voltage on R2. That is the purpose of voltage divider. But in this case, it is loaded. So how to find the R2? This one won't work anymore, right? Because this one, in this case, we do not consider R3. Or R3 equals infinity. It's not there.
Now, we're finding V2.
We are looking for R2 here.
Oh,
V2, oh, sorry, we are finding V2. And the voltage on R2. You can discuss, try to find a way to do this. Any,
And you calculate the resistance of all 1, 2, 4, then get all.
okay, let me give you a hint. Go back to one slide. Look at this one. This one looks like a loaded voltage divider, right? Exactly the same. So what I want is I want the voltage on R2.
it's the same as R2.
So combine R2 and R3.
In this table, we calculate the total current first, then we calculate this voltage drop, then we use KVL to calculate this one.
So it's
Right?
VT minus V1 for that.
Okay, Vs minus V1 in this case. But what I'm looking in the loaded voltage divider is only the voltage. I don't care all this current, all these things. That means you don't need to give me these numbers. What I want is only this voltage, V2 here. Do we have a better way to do that? Better way than you fill up this table. Time consuming, right? I'll give you another hint. Can we because we know the voltage V2 and V3 are the same, right?
Yeah.
How about if we combine these two together first.
Yes. That's what we were.
So these R2 and R3 are parallel. We combine these two first. So we are going to get something like not this one, okay. It's not a good example. This should use. Right? Our idea is we combine R2 and R3 first. Okay? Now, in your head, you imagine this is only a source here, and R1 here, and R2, 3 here. Right? Let me write here.
It's really good.
Right? It will be like this, and will be like this. And this one is R1 still. This one will be RT. We do not use RT. We use R2, 3. Right? These two are in. The value is just R2 in parallel with R3. Right? We can easily calculate this. What we want is the voltage. Right? So R2, 3 equals R2 parallel with R3. And what we want here is this voltage. This is V2, 3. We can write V2, 3, right? We know this V equals V2, which is what we want, and also equals V3. So now can you do this problem?
Vs minus V1.
Can you give me a formula? I ask you to derive this formula for this whole. Can you? Everybody try first. Look at this. Then write the formula for this loaded voltage divider. What is V2?
Do we know the number?
What's that? Vs minus V1. Is that what you
Vs
said?
minus V1 divided all by 2 because all 2 and all 3 are the same.
Oh, you cannot divide it by 2. They are the same. They must be.
We don't have that.
Anyone get this?
R2, 3 divided by R1.
Okay, let me try, and you check if this is satisfy or not. So V2, which is what we want, and we know we must use Vs, voltage divider, right? Then multiply by a ratio. Make sense? And what is on the bottom? Must be the total, right? So what is the total? The total is R1 plus R2 and R3 in parallel. Okay, what is on the top? The top is the one we are interested. So R2. Good? Are you sure?
No.
No. Okay, so look again. Okay, yes. Parallel with R3. Because this one is our interest. You imagine this one as this one here. Right? So we need to use this part here, this one. Or if you write this one is this one R1 plus R2, 3 and R2, 3 on top, like this. This is the formula we discussed before. The new things today is only this is replaced by R2 and R3 in parallel. Any questions on this? Give you some time to memorize this. the voltage divider with the resistive load is a combinational circuit, and the voltage divider is said to be loading. Okay? The loading reduces the total resistance from the node A to ground. Let's explain this one. The loading reduces the total resistance from node A to the ground. Is this true? Look at the last sentence. The loading reduces the total resistance from node A to ground. How to understand this? Is this a yes or no?
Yes.
Oh, yes? How do you know? I need explanation. You may already know. Right? For example, if I give you two resistors in parallel, can I see the total resistance is less than any of the two?
Yeah.
Or if I have like a lot of resistors in parallel, the total resistance will be smaller than the smallest of the all. Is this true? For example, I give you 10 resistors, right? All in parallel. Very simple parallel circuit.
Yeah.
These 10 resistors have different values. One must have the minimum, for example, 1K, or others equals 2K, 10K, or bigger than this one. Then I claim the total is less than the smallest.
Yes.
Yes, right? Okay, that's this what it said. If you have a load R3, so the total resistance between node A and the ground will be smaller than R2 only. So it will make it will reduce the total resistance from node A to ground. That is the meaning of this one. So that is absolutely correct, right? Okay, again, let me check if you still remember. If I have 10 identical resistance in parallel, each one is 10K ohm. What is the total resistance? 10K each. I have 10.
Yeah, 10.
Yes, I have 10Ks in parallel. What is the total?
1K.
1.
Okay.
Everybody agree?
Yes.
1, right? Yes, 1 divided by the total number, right? If this 10 are in series, it will be, I have 10Ks.
Oh.
100, right? Multiply, okay? Okay, now we are given these numbers. Right? You calculate what is the voltage across R3. R3 and R2 is the same, right? We mentioned in the formula before it's V2, but V3 is the same. Okay, now you calculate this. Give me 2 minutes to finish it, right? Everybody, you have pencil, you have paper, you have a calculator. You can do this step by step, or you can just do one step with that formula. step 1 is to calculate R2 and R3 in parallel. What is it? So just these two multiplied together, then divided by the sum. 470 times 2.2,
2,200.
2,200. I use the same unit.
Oh.
Oh,
I did the whole thing. Got to.
or you can use 0.47, right? Times 2.2. That is okay. But you need to use the same unit. Because on the bottom you need to add these two. Remember in the first homework, when you add two quantities, you must have the same unit. We need to know the formulas, and we also need to be careful. You know how to do it, but you do it wrong. Anyone get the number?
8.1.
I got
8.1. Let's see, 8.1.
Survey says.
Boy.
That is the parallel first. Anyone get this? Yes? Okay. 8.1.
Yes.
Perfect.
Yes.
Alright? That is how we do this. You can do this step by step. Step 1 is calculate the parallel of R2 and R3. You can give us this number is 387. Then you use V3. V3 equals V2, 3 because they are in parallel, right? Then that is the voltage divider we discussed before. Right? We R23 divided by the total R1 plus R23, then times the N equals 8.1. Okay, give me some time, practice this. Everybody need to be able to do this. Otherwise, you're going to have trouble to do the homework, waste a lot of time. Everybody, pass it. You can discuss with your neighbors, right? Or you any questions? Just we discuss.
Yeah.
So everybody, right? Keep working on this. If you already done, I give you a more challenge class, right? And somebody can try this, and you keep working on this.
I know.
Yeah? You keep working on this. Once you done this, look at this one. Ouch. We have a source R1, R2, R3, R4 connected like this. And what is the total key? Sometimes when you design a circuit, you do not necessarily have all the values you want. You need to combine, for example. You need 2K, but you don't have 2K, so you use 1K plus 1K, right? Not good. Suppose I give you this circuit.
How many resistors can you use circuits put for?
As many as you want.
Yeah, you can have as many as you want.
Yeah, you can.
So if I wanted, I could put 20 in one of them?
You can put 200, 2,000.
200? You can have 1,000 ohm resistors, you can have 1,000 ohm resistors.
How many transistors, for example, in the IC, integrated circuit, for example, your cell phone has a lot of ICs inside, right? The CPU is a lot of. In each IC, for example, how many transistors or you can say resistors can you imagine? How many do you have?
A lot.
Huh? Several more, like several thousand. Maybe 100,000 transistors inside that little. Right? A lot.
Are we just writing the formula?
Yeah, you write the formula how to do this. Right? The example I give you here is, for example, that means you do not need to memorize all the formulas because for different circuits you can have different formulas, right? But you need to memorize the basic ones. For example, Ohm's law, this voltage divider, this. Then you fundamental ones. Then you can easily derive the formulas for 20 resistors, 30 resistors. Who cares? You can derive anything.
I know, but what you're trying to find. What we're trying to find.
We try to find the voltage here.
Okay.
That is the voltage divider.
What is it?
Eh? Okay, good. That's good. Eh? I believe you know what is R12, what is R13. Eh? Perfect. Good job.
You were never in the childhood in the first place. So you can
Anybody?
There's no challenge.
Everyone finish this?
Yes.
Yes. Okay. So, are you interested in this one? No? Anyone interested in this? I just ask you one question. How these four are connected?
There. I know 1 and 2 are parallel.
1 and 2 in parallel.
Yeah.
3 and 4 in parallel.
Yeah.
Yes.
Or I said 1 and 3 in series. 2 and 4 in series.
Yes.
Right? So I will have several conclusions. Right? First one I said 1 and 2 in parallel. Right? Then 3 and 4 are in parallel. Then they are in series.
Yeah.
So that is the total resistance I'm trying to find out. Or maybe this. I said 1 and 2 in series. Sorry, 1 and 3. Right? And 2 and 4 in series. Then both are in parallel. Which one you like?
I like the first one.
You like the first one?
I like the first one.
You like the first one?
Oh, no, I like adding first.
Everybody like the first one?
Yeah. Second.
You kind of like the second.
I like first.
I like the first one.
Oh, we'll go with the first one, I'm sorry.
Huh?
The first one.
First one?
Yeah.
Can you tell me why you like the first one?
Because like, you look.
Don't say that. You I just like it. Okay, so why? This is you believe this is correct.
Because it's sad that R1 is parallel with R2 and R3 is parallel with R4.
And they're in series.
And,
I mean, they're both correct. I thought you were
Yeah.
saying which one we like better.
yeah.
Yeah, they're both correct.
No, they're, no.
So this one is not correct.
Wait, one's parallel,
they're both
one's
not correct.
series.
Yeah, one.
Both are correct.
The bottom one is not.
Oh, it's
Bottom
This one is not.
Wait, yeah. Yeah, they're both right.
It could be.
Both are right.
Yeah, they're both right.
I think they're both
Oh,
right.
if you plug into numbers, you have only these two numbers will be different. That means there's at least y is wrong. Right? You cannot have different values.
Yeah, that's why it's changed.
Right?
You're right.
This one is good. I like this too. I don't like this. This one is wrong. Everybody agree with this?
Yes.
You have questions? Huh? No questions?
Why is the bottom one wrong?
Okay, that's good question. Why the bottom one is wrong? I try to ask this. Okay? No one has more questions? Okay, everybody says this is wrong. Now, how do you revise the circuit to make this one correct?
delete the middle line. Yeah.
Alright, yeah.
Then this circuit
Then that's one whole, yeah.
will be,
I got it.
this one will be correct. The total resistance will be this one in series, this one, these two in series, then in parallel. This one will be, right? Make sense?
Yes.
So this one is for this circuit. This one is for this circuit. So you can see they are different. This is called bridge. We are going to discuss maybe today or next time. Does everybody get the difference? Understand that? If not, we have videos here, right? You are welcome to watch the video again, right? Okay, now suppose this one, we know this one is correct right now. I still want this. What is the formula for this VO? V out. Can you give me a formula how to calculate this output voltage? Suppose I use this one, this circuit. Now the circuit is like this. Let me ask you, do these two affect the output? For example, I change this one to the value, increase this value or decrease this value. Does this change?
No.
No. Why?
Because it equals zero.
Because this voltage here is in parallel. So this here is always equals Vs. This one is voltage divider, right? We don't care this part.
Yeah.
Right? So this is V, total is Vs. Look, this is total Vs. So Vs is only multiplied by this divided by the sum of these two. So we don't care this, we don't care this. If your circuit looks like this, right? Is this good? No? Alright, so next concept is called stiff voltage divider. Because look at that one. Ignore that R load first. That is a very simple voltage divider. We can use that formula to calculate the voltage drop on R2. Yes? We can, right? Now, if you go to the lab, you want to connect a voltmeter. We know how to connect the voltmeter, right? Positive on the top, negative on the bottom to measure this. And you are going to find, oh, that value is not correct. The reason is, first one, your calculation is wrong. Okay, you double check, it is correct, right? The reason possibly because that meter as a load will change the reading, the readings. Usually we do not want the change to be as large. So we want this change to be small. That is called stiff voltage divider. Stiff voltage divider means if you have, look at this. If you remove this one, we are going to have voltage V2, right? That's the first V2. If you have this RL here, we are going to have a second V2. We already know how to calculate this. This V2 will be different. And the second V2 will be smaller or larger? Smaller, right? Why is it smaller? Because we already mentioned on the first slide, the last slide said the node, the resistance between this node A to the ground will be smaller.
Yeah.
So that is the share of the voltage applied on here will be smaller. Right? And if this difference, the smaller, is very small, then this is called stiff voltage divider. Right? Put this very simple. For example, if this one equals 10, if this one is 1K, this one is 1K, without this load, what is the voltage here? If this one equals 10, and if this equals 1K, if this one also equals 1K. We don't have this load here. First, what is the V2 here? 5. That's easy, right? Because this one equals 1K, this is 1K, they are same. So they share this 10, so each one is 5. Right? Now, we connect it to this one. This value will be smaller than 5.
Yeah.
Suppose it is very close to 5, although it's still smaller than 5, then we call this one as a stiff voltage divider. If you connect this one, the voltage reduced to very small, for example 4, 3, or even smaller, then that is not stiff. Stiff means the voltage almost does not change. Does it make sense?
Yes, sir.
So usually in the circuit, if you measure something or you want to, you do not want to change the original value. So we want to make the circuit like this to be stiff. That is the purpose. Right? If you measure something or you change the circuit, then that's not good concept. So when the voltage divider is stiff, we read this first. When the voltage divider is stiff. You read it. Huh? When it will be stiff, yeah, the voltage drop will be small.
Yeah.
So when? Then more details.
It's when the load resistance is so
Means,
small.
look at this one. If you connect the load, there will be current flowing. Instead only to here, it will have some current flows to this way, right? And we want this current to this way to be as small as possible, to be very small. That means we want this one to be, the resistance to be very large. Right? So look at this one. RL is large compared to the divider resistance. Right? So when this resistance is large compared to this, or the current flowing through this branch is very small compared to this way, this circuit, this voltage divider will be stiff. So when you design a circuit later time, you need to make sure this one as large as possible. How large? The best way is
Get those giant birds.
you want this one to be as large as possible. So the best is infinity, which is open circuit. Right? That means you do not connect this load. Okay? Okay, now look and see. For a stiff circuit, the current flowing to the divider resistor is large, and to the load is small. Example. Oh, I use this example. R1 equals R2 equals 1K. What value RL will be make the divider stiff? What fraction of the load? Let me see something. We said we want to make the load resistance is very large compared to this one. How large? Looks like it didn't see here. The large means 10 times. 10 times, okay? Now you do this one. Calculate this one. If R1, R2 equals 1K, what value of RL will make this one a stiff voltage divider? So what is RL?
10K.
10K, right? 10 times. Didn't see somewhere here, right? Maybe in the textbook. So it will be 10K. Then, now, this is the interesting part. You need to calculate. What fraction of unloaded voltage is the loaded voltage? What fraction of the unloaded voltage is the loaded voltage? 1/10.
No, it's
That is a good guess. It is a good guess. It's very close, but not exact.
1/9.
I want everybody to calculate this. Now,
111.
you calculate.
It just keeps going.
0.9.
How about this? We make this as a quiz. Give you a bonus point.
What?
Huh?
Oh. 0.1.
0.1 over 10.
No.
Okay, everybody do this?
Wait, so
Don't guess. Do it. The result will surprise you. We said if this one is stiff, that means this I error, how much is the I error? Will be 10, right?
yeah.
So now everything is given. This one equals 1K, this one equals 1K, this one equals 10K. So all the resistance are given. What we want is what fraction of the unloaded voltage is the loaded voltage. That means you need to calculate the unloaded voltage and calculate the loaded voltage, compare these two. What fraction? The fraction is what we want. Okay? Let me help you with the simple one. What is the unloaded voltage? Okay. Unloaded voltage. Yes. The unloaded voltage. That means this one does not exist. Because half VS, right? So I solve the first one. Easy run for me.
I got 11.
Okay, now you do the hard one. What is the loaded voltage? You know how to do this, right? We have formulas over there.
Yes.
Right? We owe the output with V2 or V1. Right? So equals Vs what is on the top?
R1.
We already know the numbers.
R1.
You already know.
1,
R1. Parallel to 10. So
right?
that's 1 times.
Over 1 plus 1 parallel to 10.
Yeah, parallel to 10.
This good?
So that's 11 over 10. 10 over 11.
Okay, let's see what we have here. What is 1 parallel with 10? 10 over 11. 10 over 11. What is this? 1 plus this one is still 10 over 11. And this one will be 11 over 11, right? 1 is 11 over 11. And this add up together, it will be 21 over 11, right? And this 11 can be gone. So that will be 10 over 21. Good? And what we have before, this is loaded, right? The unloaded equals, this is loaded. The unloaded is Vs equals the unloaded equals Vs times 1 over, you get lost, right?
Okay.
Unloaded means the 10 does not exist. 1 over, the 10 does not exist.
1 over 2.
1 over 2, right? Because we have only that 2. That is what we had last time. That is unloaded, right? Which means is Vs over 20 over 10, right? This is 21, 10 over 21. This is 10 over 20. So now, what fraction? We want to know the fraction of which one is bigger? You can see. This one is bigger, right?
Yeah.
This one is smaller, right?
Just subtract.
So we want to know what fraction of this is this one. That is what we want, right? What fraction of this is this one? So we are going to use this one divided by this. Right? Yes? Can you read all this? So the fraction is, we are asking what fraction of the unloaded is the loaded. So we are going to use this one, 10 over 21. Both have VS. We divide, we cancel each other, so we don't need to care. Then divided by 10 over 20. Okay? So that will be 20 over 21. So what fraction is this? And 95. That's it? Something 95%. So you can see if the voltage divider is stiff, that means the loaded resistance is 10 times more than the divider resistance. Then we still have the voltage change, but the change is approximately equal to 5%. So reduce the to 95% of the unloaded voltage divider. Then theoretically, we want this one to be as close to 1 as possible. So how to do this? I want this one, I said, okay, this one is, the fraction is too small. I want this one to be a little bit larger. So how are you going to do this? You make this 10 even larger, right? Make 20, make it 100. Ideally, equal to infinity, then this fraction will be equal to 100%. We do not change anything because that is open circuit. Any questions on this? Good? That's a very important concept. Right? We have a theory here, and the techniques behind this theory is very useful, no matter in our labs or in later time when you work for this. So for example, when you try to measure something, you do not want to change the circuit or the system. So what you do is you want to make this system stiff. Means your input impedance, your output impedance of your, no matter equipment, mirror, or anything, to be as large as possible. So for the system you want to measure, to look at into your equipment, it will be almost an open circuit. The resistance is very large, and to not affect the system. Right, so the solution is that is the result. Right? It's supposed to be 0.5 for the unloaded. Then the loaded equals 0.476. So the fraction is 95%. Because this one asked directly what is the fraction. So we didn't come to the actual value. We just directly calculated the fraction. Right? So that. You know how to get this 0.476, right? That is this 10 over 21.
Yeah.
10 over 21 equals this number. But we don't need that now. What we want is only the fraction, so it's 95 directly. Okay, so now if you go to the lab, look at this. The source is 10, and that one is 470, the other one is 470. What is the unloaded voltage on the R2? Suppose this is in the lab, right? Okay, so what is the voltage you expect on the R2? 5, right?
Yeah.
But if you measure it, what do you expect?
Lower.
Lower than 5, right? Right. So actually, it is 4.04. 4.04. If you look at both, 4.04, 4.04. Are you surprised? Is KVL still satisfied? 4.04, 4.04. Add up together, not equal to 10. Anything wrong here? Yes, if you measure this, see? If you measure the total equals 10. Measure this one, 4.04. This one, 4 also. 4 plus 4 equals 8, but the total equals 10.
Resistance in the cable?
Resistance to the cable, oh, that is a good imagination. I don't know. What happened here? I want reason. Anyone knows why?
The meter is counting as a resistance.
Yes, the needle.
The needle.
So what happened here? I ask this: is KVL still good?
Yes.
You need to believe in that. That is the law. So if this one equals a 4 on the top, what is the voltage on the bottom? 6, right? Need to be 6. But you measure it, it is 4.
Voltage source is trash.
What happened? I'll ask you, okay? You will, I will leave this one as a question.
Internal resistance?
Everyone knows the problem, right? The total is 10. You want each one is 5, but if you measure it, it is 4. Eh? Then you measure the next one, still 4. 4 plus 4 equals 8, not equal to 10. Where does that do? Some resistance, no. Wires, no. Okay, that's not the reason. Right? I leave this one as a question for you to think. Then
Next class?
today is Tuesday, right? We don't have class Thursday. No, not because of the resistance. Consider the loaded divider. This concept we are discussing loaded cells.
I just see my face. Stop. They put my face here. Watch the video.